Hello everybody and welcome to this talk. My name is Luis and I am part of the Babel Research Group at the Universidad Politécnica de Madrid. In this talk I am going to present you Machina, a new quick check state machine library. First, I will briefly introduce you to property-based testing. Afterwards, I will go through the evolution of property-based testing state machines, and the rest of the talk I will be focused on Machina and the features it brings to quick check state machines. So let's start. Testing is the most widely used technique to ensure quality of software. Usually, testing is performed using a technique called unit testing, a technique that consists on defining tests one by one. For instance, imagine that you want to test a simple function that computes the reverse of a list. Just for this very simple program, there are infinite possibilities, so we can conclude that unit testing is hard. But nothing to worry about, because QuickCheck comes to the rescue. QuickCheck is a property-based testing tool that completely changed the testing paradigm. QuickCheck brought a new philosophy to the testing sphere. Don't write tests, but generate them. A test in QuickCheck is called a property, and the execution of a property is divided in three phases. First, we need to generate the data necessary for the test execution. Then, we check that the generated data satisfies the property predicate. And finally, if the test fails, a shrinking strategy is executed to retrieve a minimal counterexample. Let's now take a look at a property on reverse lists. As everybody knows, when we apply the reverse function to a list twice, we get the original list. This can be translated as the following QuickCheck property. This is not the best property to test a reverse function, since it also checks the identity function, but it will help us to illustrate how QuickCheck works. This property will potentially generate an infinite amount of lists using the list generator. Each generated list will be checked against the property predicate. If the predicate is not satisfied by one of the outputs, QuickCheck will shrink the data and return a smaller counterexample. So property-based testing is a very powerful tool to improve our tests. And this simple approach works perfectly with purely functional programs. Unfortunately, not all programs are purely functional. But don't worry, QuickCheck has support for stateful programs. We just need to introduce a couple of concepts. So what do we mean by a stateful program? A stateful program is a kind of program in which the result of its execution depends on the previous interactions with the program. To illustrate how to test stateful programs, we will use a counter. This counter will have a very simple API. First of all, we need commands that permit us to start and stop the counter. We also need a way to modify the value of the counter. To modify the value of the counter, we will have an operation to increment it and to set it to a certain value. Finally, we need a way to check its internal value with some accessing function. So this is the shape of the API of the counter. It's interesting to notice that all commands are stateful except get. And it is also important that stateful commands don't return the value of the counter. So the only way to fetch its internal state is by using get. So if we want to write a unit test on this program, this could be a possibility. How can we represent this unit test as a state machine? It should not be very difficult. A state machine representing this test will have the counter state as the state of the state machine and the commands executed as transitions. First, the invocation to start initializes the state machine. Then, we increment the value. The get command does not change the state. We set the counter value to 4. Again, get doesn't change the value, and the test is done. Viewing this, what do we need to test a stateful program correctly? First of all, we need some way to generate sequences of commands. We also need a symbolic state to track the evolution of the system. And finally, we need a way to specify how to interact with the program during the tests. Now let's take a look at how to test a stateful program using property-based testing. The first thing we need to do is to write the property that we want to check. The property we want to check looks something like this. This property is composed by two main parts. The first one is the command generator that will generate sequences of commands of a given state machine. In our example, we'll generate sequences of the commands available in the counter. The other part of this property is the function runCommands. RunCommands will execute the generated sequence against the program that we want to test. It will also check the result of every command execution against some predefined postcondition. Now let's take a look at how runCommands works. Let's take the first generated sequence to illustrate the behavior of runCommands. First of all, the increment is executed and returns OK. This result is checked against some postcondition. As we previously said, there is not much information we can check here, so the postcondition is always true. The next call is executed, this time is a get command. This time there is something we can check in the post condition. The value returned by the call must be the same as the value pre-computed by the symbolic state. Now it is time for the put command that sets the value of the counter to 4. Again, nothing that can be checked in the post condition. And this is the last call to get that returns a 4, which is again checked with the symbolic state. And the test is finished. The place where all this behavior is specified is what we call a quick check state machine or a quick check model. So now let's take a look at the evolution of quick check state machines. The original way of defining quick check state machines was what we will call callback function style. It was developed by Cubic in their Erlang quick check library. The behavior of these state machines was specified using callbacks. The first callback, called initial state, corresponds to the initial state of the symbolic state of the model. In our running example, this is just the value 0. The second callback, called command, specifies how to generate symbolic calls to the program under test. In our example, we are only going to generate calls to increment, get, and put for the sake of simplicity. It is important to notice that arguments generators are specified together with the command call. In our example, we only need to generate integers in put calls. The precondition callback specifies whether a generated symbolic call can be used on a certain state. In our example, we allow calling all commands in any moment of the execution. The next state callback is used to compute the next symbolic state after a given symbolic call. In our example, we have two functions that modify the symbolic state of the model, increment and put. The postcondition callback checks that the result returned by the program under test satisfies some predicate. In our example, the only command that can check something is get. That will check if the result returned after the call is the same as the symbolic state computed by the state machine. This first version of the quick check state machines presents some problems. First of all, contains some boilerplate code that can be automatically generated, but also makes hard adding new commands, requiring the programmer to rewrite the callback functions. These problems make these state machines hard to extend and to maintain. The next generation of quick check state machines was also developed by Cubic. These state machines move the focus of the previous callbacks to the state machine command. This means that the behavior of the state machine is defined in terms of the behavior of its command. In these state machines, each command should define a precondition that makes the command available. In our example, it is true for all commands, so we can omit it. A generator of command arguments. In this generator, the result should be put in a list. In our example, put is the only command that needs some argument generation. The callback pre is necessary to control the shrinking process. Since we are not talking about the shrinking in this talk, we will omit it. We also need a command that calls the real implementation. The postcondition callback defines the predicate that should be satisfied after the execution of the command. In our example, this is only necessary on get, as we have previously seen. And finally, next computes the next symbolic state, and it is necessary to keep track of the changes performed by the stateful operations. In our example, we only need a next definition on increment and put. This domain-specific language to implement state machines achieves really important improvements. First of all, reduces the amount of boilerplate necessary to write state machines. Also makes much easier to include new commands. Despite its improvements, this way of defining state machines still have some drawbacks. Errors in state machines are caught at runtime and are hard to debug, and still there are not built-in support for code reuse. So now we will take a look at Machina. Machina is a new domain-specific language to write quick-check state machines in Elixir. It was inspired by the state machine DSL available in PropCheck. Machina aims to improve development of state machines in various ways. First of all, we want to improve model quality with an earlier error detection. Also, we want to reduce the amount of boilerplate necessary to write models. In Machina, we want to improve maintainability of models. And finally, we want to make it easier to reuse code of quick-check models. To achieve these objectives, Machina will provide a new declarative syntax for command definition and state definition. It will permit automatic access to parameters and state attributes inside the command declaration. On top of this feature, will provide better support for typing state machines. And finally, we will introduce some built-in mechanisms for model extension and model composition to facilitate code reuse. So how Machina works? Machina is implemented using Elixir macros. and exposes 3 macros that should be used by the user to define a state machine. DefState allows the user to define the attributes that will be included as the symbolic state. DefCommand is used to define commands in the state machine. And finally, the use macro, which is necessary to configure the module that defines the state machine. Commands in Machina are defined in the previously showed command style, but with 2 main differences. The command prefix is no longer necessary, and we decided to rename the command args2 to valid args to make it clearer. Now let's re-implement our counter model using Machina. First of all, we must configure our model with the use macro. This will import the rest of the macros necessary to implement a Machina state machine. Notice that we use the implemented by construct. This construct allows us to redirect command calls to the module under test. During macro expansion, Machina will introduce the calls to the module where necessary. To define the symbolic state of the state machine, we will use DefState. This macro receives as arguments a keyword list of attributes. Each of the elements of this list has the name of an attribute and its initial value. Optionally, the user can provide typing information to improve error detection. The last part of a Machina definition are the commands. Each command declaration contains the command name and its arguments. Like in state attributes, arguments in commands can be provided with type information. Finally, the body of the command contains the callbacks that define its behavior. So what are the advantages of this definition? First of all, it gives an easier interface to type specs, which is highly beneficial for the quality of models. By explicitly naming state attributes, they are widely accessible in commands. What is also true in parameters in commands. This has 2 main advantages. First, as documentation, and second, reducing the arguments in callbacks. The implemented by construct is very helpful to reduce the necessary code in state machines. Other important difference with previous state machines is the decision of using maps in the argument generation instead of plain lists. This is mainly to avoid ordered problems, but it also helps catching errors at compile time, if for instance an argument generator is missing. This is also applicable to the symbolic state, as with arguments it always uses maps. This allows, for example, to notice if a map is not correctly updated. So far we have talked about how Machina tries to make state machines less buggy, but we haven't talked about one of the major drawbacks of traditional state machines, their lack of extensibility. Machina provides 2 new built-in mechanisms for extending models. These constructs will permit us to separate different modeling concerns in different models and divide a model into smaller parts corresponding to each of its features. It also allows us to compose submodels into a bigger model. This way, a model can be easily maintained in parallel with a project that integrates features iteratively. And finally, it permits the reuse of models. These mechanisms are model extension and model composition. They will be developed in detail in the next slides. So what do we call model extension? We will say that a model extends another when it is written in terms of it. To illustrate extension, we are going to split our model in 2 models. Each of these models will be focused on a different phase of the testing process. We will call these new models generator and judge. We will start by the generator model. Generator is our base state machine. It focuses on argument generation and command execution. By looking at the example, we can see that the generator does not check any postcondition, neither changes the symbolic state, since it is not needed to generate new values. Now, we will write the judge model which extends generator. This model is focused on correctness checking, so it needs to keep track of the state changes using a symbolic state, and also needs to check the postcondition after calling it. So what is going on when a model extends another? Firstly, the state definition in the extended model is the union of all attributes. Secondly, the commands available in the extended model are also the union of all commands. And thirdly, callbacks have different behaviors when they appear both in the original model and in the extended one. If a command appears in both models, the definition of pre-args call or valid args in judge will override the definition in generators. The behavior of post is a bit different. Instead of overriding, when judge redefines a post callback, the conjunction between both definitions must be checked after the test execution. In addition to this, the user may want to access definitions from generator in the judge definition. This can be achieved using the super function, which is accessible in all callbacks. So this is the extension mechanism that Machina provides to the user. Now let's dive into parallel composition. Parallel composition will allow us to merge any number of models together. To illustrate it, first we are going to split the original model in 3 submodels, 1 model per command. With these 3 models, we can write a new composed model. To create a composed model, we need to use the extends construct again. This time, instead of a single model, extends will receive a list of models to compose. The result of expanding this macro will be a new composed model that follows some rules. The state of the composed model is the union of all attributes in the submodels. The commands available in the composed model are the union of all commands defined in the submodels. Until here, the behavior is very similar to extends. Things change when a command definition is repeated in various submodels. Postcondition of the callback in the composed model is the conjunction of all postconditions in the submodels. But this time, also valid args is the conjunction of all submodels callbacks. This is necessary to be able to string correctly a counterexample. The next callback will be defined as the composition of the next callbacks defined in the submodels. This means that the resulting symbolic state will be the result of applying the next callbacks of the submodels. The application of the next callbacks is performed in order of appearance in the list provided to extends. The precondition callback in the composed model is the disjunction of all the callbacks in the submodels. This is because we need just one true precondition to be able to generate arguments. The arguments callback will perform a random choice of the submodel callbacks. This random choice will be between the callbacks in which preconditions are true. Finally, if more than one implementation is defined for a given command, it is randomly selected at the execution time. The postcondition of a command can be refined by defining new postcondition in the composed model. This way, the resulting postcondition will be the conjunction between the postcondition of the composed model and the new postcondition. So we arrive to the end of the talk. As conclusions, we have to say that property-based testing has become very popular, but the state machines based on property-based testing are less common. We think that quick-check state machines are a really powerful tool for testing, but as we have seen, present some drawbacks that maybe are slowing down their adoption. Models are often buggy and hard to maintain. They don't provide an easy way to reuse code. In Machina, we try to address these problems by providing built-in support for type definitions and with 2 built-in mechanisms that allow code reuse. Finally, I want to remark that Machina is still a very experimental library, and we still are changing things on a daily basis. We have found some problems with our type definitions generated by Machina that were not spotted by the current type checking tools available in the Elixir. More concretely, has to do with types generated for the next callbacks and the arguments generators used in the state machines. We are not fully sure that the semantics of composition respect subtyping, and we also think that the new constructs are too expressive and permit the user to do things that he shouldn't. We are also improving Machina. For example, we are currently adding new operators that can be useful as command renaming. And finally, we want to revise the callbacks that are available in Machina commands, as some of them look intrinsically related, like precondition and argument generation. So that's all for the talk. Thank you for listening, and I hope you enjoy it.